Hello, guys. I hope you're doing great today. Welcome to MJ School of Mining and Geology. In today's lesson, we will learn much about the crystal defect. Okay, we want to understand their causes, their types, factors, and their importance in mineralogy. Please do not forget to like, share, subscribe if you haven't yet subscribed to our channel, and do not forget to hit the ring bell below so that you are notified each time we upload new content. So we need to understand first what is a crystal, okay, and then its lattices or the lattice point, because for you to understand the crystal defects, you need to understand that the crystal, it's a solid material with the molecules or the ions or the atoms. But now these atoms or the molecules of the atoms, they fit together in a repeated pattern in all directions. All right. But now, if we were to take now a portion of this crystal, we're going to have what you call a unit cell. A unit cell is what you call the building block of a crystal. It means for us to have a crystal, we need a unit cell. So this is a unit cell. So it means a crystal is made up of repetition of unit cells. And then within those unit cells, you've got the atoms, which also they tightly fit together in a repeated pattern in all directions. Now, but now, if you were to remove the atoms, the actual atoms, and then put some points or some dots, and then we create what you call the lattice. Okay, so an ideal crystal, the imaginary crystal, it comprises lattice and motifs. Okay, now where in the lattice, it's a 3-day periodic arrangement of points, and then a motif is just an atom or group of atoms. Okay, so you need the understanding of what exactly is the crystal. Okay, sorry about that. Now, the crystal defect, on the other hand, okay, now you understand what a crystal is. Now we want to understand the defect. Okay, so the real crystal, they deviate from ideality. So remember, an ideal crystal comprises the lattice and the motifs. Okay, they are like that. So, but now remember, that is an ideal crystal. It means in the real world, that kind of a crystal, it's unlikely for it to be like that for its entire existence. Then now it means because of the geological processes, tectonic deformation, faulting and folding, and many other geological processes, okay, we're gonna now form or to cause the minerals or the crystals to defect, okay, or to change their shape or to be imperfect. So this deviation from ideality is called the defect or the imperfection. Okay, because the perfect crystal, it's the one that it is not affected by anything. It just has the crystals. It's just has those atoms or the motifs and of course the lattices. So the crystal defects, now it controls the physical and mechanical properties of minerals. Okay, structural defect plays a significant role in influencing the properties, behavior, and the stability of minerals. For the minerals to be stable under certain conditions, how the mineral behave, and of course their physical properties, it's influenced by this structural defect when you're causing the crystal to be imperfect. Okay, now it is important for us to understand this crystal defect, because now if we understand this crystal defect and we are able to characterize them, okay, now we will be able to understand and interpret the physical, chemical, and mechanical properties of minerals. Okay, now if we understand those properties, we know exactly where a certain mineral can be applied. Okay, some minerals, they are conductive, some minerals magnetic, and many other physical properties. So we need to understand these properties to know exactly where we can use this mineral for certain applications, okay, in the real world, of course. Now, structural defects in mineralogy, it refers to a deviation from ideal atomic arrangement, okay, within the crystal or the crystal lattice of a mineral. I hope up to so far now you understand what this crystal defect is. You are moving away from an ideal atomic arrangement, because in unreal world you'd have now those atoms that are packed nicely, fit nicely within a unit cell of a crystal in a repeated pattern in all directions. Okay, now they're gonna be untouched in an ideal world, but in the real world, okay, now those atoms, they will be shifted, rotated, and deformed. Okay, and then that's what you call them, the crystal defect. You are deviating away from there, or you're deviating from there, the ideal atomic arrangement. Now, this defect can occur during crystal growth, then phase transition, or due to external influences such as pressures and temperatures. Um, um, in one of our lessons, please, you are advised to go and check it. We have a video on the crystal growth. What exactly are the crystal is the crystal growth? I mean, the crystal growth, we start with the nucleation, and then once we've got the seed or the nucleus, and then the crystal will start to grow. And then as it grows, it can be defected, or it can be twinned. And then we also have the lesson involving the twinning, the twin laws, the types, and the mechanism for twinning formation. Okay, so you need to understand that as the crystal grows, it might be defected, it might be twinned, and be affected by other geological processes. Okay. Now, without any further waste of time, we now want to classify them, the defects or the crystal defects. But now, this classification is based on the dimensionality. Okay, so if we have, that is to say, if we have got a 0 dimension, if we have got 1 dimension, or if we've got 2 dimension, then in today's video, we're gonna talk and explain these types of dimension, or types of the defects found within first or 0, first, and second dimension. So in the 0 dimension, if you don't want to say 0 dimension, you can say point defects. Okay, so example of point defects, we're going to talk about the vacancy, the interstitial, and the substitutional defect. Okay, and then 1 dimension, if you don't want to say 1 dimension, you can say line defect. For example, dislocations. We've got 2 types of dislocations. We've got the screw or the edge defect. And the last but not least, we're going to talk about the surface defect. And then with the surface defect, we can talk much about the free surface, the grain boundary, the twin boundary, the stacking fold defect. So without any further waste of time, let's start with the 0 dimension. If you don't want to say 0 dimension, you can say point defect. And then point defect involve deviation from the ideal atomic arrangement at a specific lattice point, because it's a point defect. You are caring much about that particular point. So at a specific lattice point within the crystal structure, at exactly that point. You remember I showed you a crystal, an ideal crystal, and then after that we instead of putting in the real atoms, we put the points or the lattice points. And then if you're gonna now deviate the ideal atomic arrangement at that particular lattice point, we're gonna form this point defect. And we've got three types. We've got Squeakle, and then Frankel, and Puritan. And then more common types, it include the vacancies, interstitial, and substitutional defects. And these words, they are self-explanatory in sense that vacancy, it's more about the space, and then interstitial within the pore spaces, substitutional, something gets out and the other thing gets in. I'll always I like to give example with soccer, because for example, when you are substituting a player, it means you are putting or you are placing in the player with the same characteristics, but that player has more energy or has much to offer as compared to the one substituted. So nonetheless, vacancies occur when the lattice sides within the crystal are unoccupied by atoms. We've got the free spaces, the vacancy, we've got the free spaces, okay? So those vacancies can result from the thermal vibration or intrinsic defects during crystal growth, okay? We're going to talk about these intrinsic defects not so long. So thermal vibrations due to thermal vibration or the intrinsic defect, we can have some vacancies, okay? So we can have the spaces which are unoccupied by the atoms or the ions. But interstitial, atoms or ions that occupy interstitial sites between the regular lattice points, these defects can arise due to impurities, radiation damage, or diffusion process. And then last but not least, we've got substitutional, as self-explanatory, like I said. Okay, so these occur when atoms or ions of one element replace atoms or ions of another element within the crystal lattice. Okay, so this substitution can lead to changes in the chemical composition and properties of the mineral. Okay, so for example, substitution, this has got the same analogy with substitution solid solution. So you are changing what you call the chemical composition, because now for example, if you have a limestone, for example, all right, then remember, a limestone, it's calcium carbonate. But now if you introducing the magnesium into that limestone, you're gonna form what you call them the dolomite. Now can now see that you are changing the composition of that particular mineral. All right, so remember the vacancy, it means that the atoms or the ions, they are unoccupied. The side are unoccupied. This side were supposed to be occupied by the atoms or the ions, but now they remain vacant, means we don't have any space. Okay, so like we said, about their causes. And then interstitial, you are coming in with something new and then placing it within the pore spaces, or within the interstices. Okay, then the substitutional, I mean, you come in with something and then you remove something and put something new. Okay, that is substitutional. So you can either substitute larger crystals or larger atoms, sorry, and or you can substitute smaller atoms. Okay, so with Frankel, you remove something and then put something somewhere. Okay, you take it somewhere and then you place it somewhere. So this was initially here, this atom was initially here, and then you remove it, making this place to be vacant. Okay, creating a vacancy, and then you are placing it somewhere new, and then by so doing, you are now changing the behavior of that particular crystal. Now, line defects or two dimensions. one, sorry. Okay, so we're talking dislocations. Like I said, we've got the edge dislocations or the screw dislocation. So with this screw dislocation, you are now sharing or you share the displacement. You can see here, you share displacement of atomic planes within the crystal lattice. Okay, but now along a specific axis. Okay, so or along what you call them screw axis along this. Okay, can you now see? So you are sharing that. So screw dislocation involve a shear displacement of atomic planes within the crystal lattice along the specific axis. Screw dislocations can contribute to plastic deformation and slip in minerals. Then now the edge one dislocation occur when there is an extra half plane of atoms or ions inserted into the crystal lattice along the edge. Okay, along the edge. Edge dislocation can affect the mechanical properties of minerals, such as the strength and ductility. Okay, so can you now see that if you share this along its screw axis, you are forming what you call the screw dislocation. Remember, to dislocate, you to dislocate is self-explanatory. Something that was at its own location initially, then you move it, okay? Obviously by geological processes, okay? Then now you form a defect. Now with this one, you pushing it like that with this one edge dislocation. Now planar defects, we talk about twin boundaries. Okay, there are two. We've got twin boundary and stacking folds. Okay, these are more interesting. So the twin boundary, they've got the same analogy with a mirror plane. They've got the same analogy with the mirror plane in twinning. All right, so then the crystals, they share the same twin plane on the mineral plane. Okay, so twin boundaries separate twin crystal domains and result from twinning process during crystal growth. Okay, so twin boundaries can influence the optical, mechanical, and electrical properties of minerals. Okay, so if you share the boundary, then you result in what you call the twin boundary. Then stacking fold, which is in simplest terms, stacking fold, it's a fold in the stacking sequence of a crystal. So if we were stacking, for example, a cubic closed packed structure, we call it a CCP, cubic closed packed structure, and then each of those, we're gonna call them the plane. I'm going to show you what we mean. And then these planes are displaced with respect to each other. Then from a three-plane repeated sequence, we can have ABC, we can have CBA, CBA, or ABC, ABC. So it doesn't really matter as long as we've got these three-plane repeated sequence. But now, for example, if we say ABC, 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 it's a repeated pattern. But immediately when we say ABC, then ABC, then BC, A, then we know, oh, A, it's, what did I say? I say ABC, ABC, then A, C maybe, then we know B is missing. So then can you now see that you have disturbed the stacking sequence. So this is the stacking fold. Fold boundary occurred when you took the plane out. Then now would refer to that as the stacking fold. It's very interesting. For example, let me show you something. We've got the 3D repeated pattern, ABC, 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 ABC. Can now see? But now look at the pattern, ABC, AB, C, and then I expect ABC, but now there is B. Then something is missing. Then we say that is a boundary, is the fold boundary. Something is missing. But now, then it was supposed to be ABC, ABC, and then A. Oh, it means A is missing because it's A, B, C, then A, B, C, A, B, C. So A here it's missing. All right. So we call that a stacking fold. So um, by visualization, I hope now we can go through this slide. Then it will make even more sense. Okay, stacking fold. Okay, when there is a deviation, remember defects, you are deviating. Okay, you are deviating from an ideal atomic arrangement. Okay, so when you when there's a deviation from the regular stacking sequence of atomic planes, ABC, 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 immediately when you deviate from that, when you disturb that repeated pattern, okay, then you are causing a stacking fault. Now, stacking faults can affect the crystallographic symmetry and stability of minerals. Okay, specifically, a stacking fault arises when there is a displacement or misalignment of atomic planes along a specific crystallographic direction within the crystal lattice. I mean, now these ABC, they are defined as planes. They're defined as planes. So if now, okay, we're here. So like I said, the stacking fold arises when there is a displacement or misalignment of atomic planes. So atomic planes, we talk about those ABC along a specific crystallographic direction. Okay, so stacking folds commonly occur in minerals with layered or close packed crystal structures. Okay, such as metals, metal alloys, and many other things. They can result from various processes during crystal growth, phase transitions, or mechanical deformation. I mean, up to so far, you can see the trend that this deformation, it happens as the mineral is growing and it's transforming, or there is a mechanical deformation. And we talk much in other videos about the crystal growth and also the crystal deformation, transition, growth, twinning, and then also many other things. So please, you're more than welcome to visit other videos. Okay, so up to so far, now I hope you understand what this stacking fold is. Then now the boundary between the regular and irregular stacking sequence is known as the stacking fold plane. Now between a perfect and imperfect stacking sequence, remember when we say it's perfect, we expect ABC, ABC, ABC. But now when it becomes imperfect, remember defect is imperfection. Then when imperfection happens, now we would have something like ABC, AC. You know, then now that boundary that separates the perfect from the perfect from imperfect, we call it stacking fold plane. Okay, I hope you understand now. So I did not want to go much into greater detail. Yeah, but if you are into a mineral or material science, and then there's more you can go into, talking much about the CCP of cubics and also the is it FCC, yeah, something like that. Yeah, you have to go into deeper, into greater detail. So as for us mineralogists, would stop here and then just have the general background of what exactly is happening. Nonetheless, volume defects, it's self-explanatory. You are decreasing or you are tampering with the volume of that particular crystal. Okay, volume defects which involve irregularities or disruptions in three-dimensional space within the crystal lattice and include the grain boundary, the pores, and the voids. Okay, so in simple terms, remember the pores and the voids, we just mean the empty spaces. Okay, and then the grain boundary, it's the same as the plane boundary. So with the grain boundary, it means it's the boundary between two grains. For example, this is a grain, this is grain. Then now what separates these two grains, it will call we're going to call it a grain boundary. So in the grain boundary, The grain boundaries separate individual crystalline grains within a polycrystalline material. Grain boundary can influence mechanical strength, diffusion rate, and grain boundary migration in minerals. So, I mean, this is self-explanatory. Grain boundary, it separates two grains. But now pores and voids are spaces or cavities within the crystal lattice that are not occupied. There are vacancies occupied by atoms or ions. Pores and voids can affect the density, the porosity, and the mechanical. Okay. And so, for example, if we've got so many pores, it will have less density. But if we reduce these pores by let's say because of the weight of the overlying pressure, like for example in sedimentology, we know because of the weight of the overlying pressure, what are you doing? You are shrinking or reducing these pore spaces. Then by so doing, you are increasing the compaction and the lithification, making that rock now to be more dense. So it has got the same analogy with these crystals. Okay, now formation mechanism. Like I said, we're gonna talk much about the structural defect, or how do they form. Okay, so in one of the slides we mentioned the intrinsic processes. So these intrinsic defects arise or come from inherent imperfections in the crystal lattice during crystal growth phase, transition, or cooling. And then extrinsic refers defects result from external influences, okay, such as temperatures, pressures, and radiation. Okay, so I hope by now you understand now the difference between the two. With extrinsic, external conditions such as pressures, temperatures, and many other things, and then intrinsic, it will happens internally as the crystal is growing. Now, diffusion process can introduce point defects. Okay, diffusion process can introduce point defects such as vacancies or the interstitials into the crystal lattice by allowing atoms or ions to migrate through the lattice. Okay, so because of the point defect, now you're gonna remember we talked much about the interstitials, substitution, and these vacancies. So this diffusion would make that point defect, or the point defect to be possible, or the zero dimension defect to be possible. All right. Annealing process involve heating and cooling, okay, and can influence the formation and annealing of the structural defects, affecting the stability and the properties of the minerals. Now, we've been talking about the defects. Now, what are their effects on the properties of certain minerals, or actually properties of minerals? Okay, they first and foremost they influence their mechanical properties. So structural defects such as dislocations, grain boundaries, and stacking folds can affect the mechanical strength, the ductility, and the deformation behavior. Again, when we say ductile, it means it must conduct something, okay? And then mechanical strength, whether it can withstand some high pressures and temperatures, and deformation behavior, okay? So then electrical properties, point defects, and impurities can influence the electrical conductivity, conducting behavior, and electronic property. Okay, these point defects and the impurities. Okay. Now the optical properties, twin boundaries, stacking folds, and grain boundaries can affect the optical properties, their birefringence, and coloration of minerals. Chemical reactivity. Structural defects can influence the chemical reactivity, surface area, and the catalytic properties of mineral by providing reactive sites and altering surface morphology. So, they are just self-explanatory. I just wanted to bring this to your attention, that we don't just study these defects, but by understanding them, we're going to understand much about the minerals and where exactly we can apply those minerals because of their respective properties, which now those properties were brought or yes, were brought to that crystal by during its growth, either by this defect or by twinning. So, like I said, also go and visit twinning, and you're gonna understand more. Okay. Now the thermal stability, withstanding intense temperatures. Structural defects can affect the thermal stability, phase about that phase transition, and transformation kinetics. Okay, so I hope you understand now. In the end, we have to be able to characterize and analyze the structural defects. So the structural defects, we can use what you call the TEM, XRD, SEM analysis, and the AFM, and then also EELS. So there is the analytical or the experimental techniques that we can use to find these structural defects. For example, with transmission electron microscopy, this will allow for high resolution imaging and analysis of atomic scale defects, dislocations, and interfaces. Now, can you now see that each and every analytical equipment, because of their advantages, or because of their basically their advantages, and then those advantages, they would help us to know where we can apply or we can use them. Okay, so for example, if we want to know much about dislocations and interfaces, then we can use this TEM. All right, we can use this TEM. But now for XRD, we'll provide information about the crystal structures, lattice parameters, and stacking folds in mineral through the analysis of diffraction pattern. This is very interesting. The XRD, it's very interesting. And then the SEM enables imaging and analysis of surface morphology, grain boundaries, and defects. Okay, so and then AFM will allow for the visualization and the characterization of the surface, topography, defects, and atomic. In the end, this would allow for information about elemental composition, elemental bonding. Can now see that each and every analytical equipment has got its specific application. Okay, so they have got their own advantages. So it means it will be unfair. Okay, you might not have the best resolution if maybe you want to understand you want to have high resolution imaging and analysis of atomic scale defects and dislocations and interfaces. You use the SEM. Okay, it might work, but some of the things they're gonna be undetected. Okay, so you must use the right analytical machine. In the end, ladies and gentlemen, we are very thankful for joining us today. Your support means a whole lot to us. Keep on supporting us, keep on liking, sharing, commenting, subscribing, so that we grow this channel. Okay, we are really thankful, and we don't have much to offer, but we'll always say thank you. Until next time, cheers.